Okay, so the previous conversations, kind of depending on what level you're viewing this at, is kind of what your job function, where you're at in the organization. Somebody at the top, the owner of the company, the board, the whatever, decides, hey, we need to make these. We need to make a lot of them. Or, hey, for our one system as a prototype, we need to make a couple of these, and we'll go through the analysis as we get through the prototype, the preliminary production run, and go through. So it gets handed off to engineer's designer. Here are the design specifications. We end up with a working document. That working document should go through review, which is kind of all of you. You're watching me throw out these numbers and looking at these tolerances and trying to put the pieces of the puzzle together of how this thing is going to stack up. And at the end of the day is I walk out to the machine shop floor, and I have 10 machinists in here, and I hand each one of you a print and said, get to work, make me some of these. And your first job is to read all of this and digest and decipher what all of this is going to do. And then at the end, we pick out a couple people that are going to be the inspectors, and the inspectors look at the print, and from their perspective, they're seeing this different than what the machinist, what the designers, drafters, what the engineers, and the powers that be in the company see. All right, so this is all multifaceted looking at, and as a communication tool, as it travels through all those levels, the end product is we need one of these sitting in front of us that is functional. All right, so to do that, we have gone through, we've done our second or third revision, we've done a couple of different dimensioning strategies. Some of them are a little bit busier than others, and we've tried to follow the Y14.5 2009 2014 rules to the best of our ability, to the best of what the standard is going to do for us. All right, so at the end of that, we have made a couple of changes because revisions always come, and so putting the slots in, those are optional for you. If you want to draw those in and create them, that was one of the reasons it was included. And kind of as knowing that we have the range in the class of haven't used SolidWorks, haven't really used the dimensioning, haven't used GD&T, even as theory, that what I'm planning on doing is I will save this file out as a stripped down version. You will have all of the views, and then it'll be your job to pick a dimensioning strategy and basically reproduce what's here, but not have to go through all of the setup, have all of that, all of those pieces to the puzzle. If you've been following along and you've worked through this, you're almost done, because hopefully I'm almost done. Now the other side of it is that we still have DIM Expert MBD to get into, and that takes it in a slightly different direction, which I'm hoping to finish out tonight, so that our next assignment, next project, will be more of here's just a couple of pieces, and you'll be able to build those up and explore on your own with with the assistance, that you can kind of see and think through that process outside of following a video or following the instruction. Okay, so that's kind of where I'm looking to go, and so I'm going to open up this this sheet. I did get the assembly. I did get the bearings, and I was looking for the class of fit. So I'm going to have to find my electronic PDF version of the Machinery's Handbook so I can grab a quick snapshot and properly annotate and all that kind of stuff. Show you where these numbers actually came from. We did the bearing fit early on, so let me open up the pulley. Oh, that was the bearing. All right, so bearing comes up. It has its standard tolerances: the plus nothing, minus the 5 or 6 tenths of a thousandth, and we looked at those numbers. And then in that that chart that I was referring to, the FN1, which is a force fit, it has a range, and it says a light fit is from 0.2 of a thousandth to 1 point, or let's see how is that, a thou and 1/10. All right, and then a heavy is from about a thou to a thou, almost 2 thousandths. So thou and 9/10. All right, so how to, I'm not, I don't really want to start just throwing them out at tenths of a thousandth, 19/10 of a thousandth. That freaks me out already. So as we go through the numbers, they're very small differences. And so depending on how this tolerance and what the bearings come in at, end up interacting and playing so that we have that allowance for the force fit. That both of those end up at their maximum material condition, the largest bearing size and the smallest hole size, then I could have a medium fit of about 2 thousandths between these. And I think we calculated out at about a thou and 6/10, or maybe a thou and 8/10. All right, so I'm pretty comfortable with this number, and since I have the bearings and can put a micrometer on those, then I can get a reasonable number and know where I'm going to land on these. And like I said, for 2, I order 2, they show up on my doorstep, and I measure them, and we're not looking at a manufacturing range or a specification that's really going to use up that 0.6 of a thousandth tolerance in the bearing. But again, it comes down to the question that we always ask in the CAM class: what's it made of, and how many are we making? If we're making 2, great. If we're making 10, put a little more thought into it. If we're making 100, 1,000, 10,000, we're going to make these for a long, long time. I have to take all of those into every one of those tolerances into consideration much more seriously. All right, so to that end, I kind of discounted, and we did all of this as a top-down assembly. So when you're looking at these, all of these arrows and the virtual components, the standoffs were still minus, and I'm not worried about those being underdefined, because the first standoff was drawn in context in its location, the others were brought in, and so the only thing these you can really do, and you can't see it for the most part, is spin. All right, so I'll worry about those or let those spin a little later. So in the decision process, I decided, rather than getting a shoulder bolt that'll slide through there and that I can't really control the tolerances on, I'll just go ahead and make a piece. So I'm going to go back, let's see if that'll come up, and if I can find my example. All right, and we had the ball bearing, and so its ID tolerance is 375 with a minus 0.3 of a thousandth. And then the housing ID, for the housing ID, so they actually gave us our number, 875 minus, so that means it's actually a plus dimension. So since I didn't read that correctly, right? So for the housing ID, 7/8, OD of 875 with an OD tolerance of minus 0.4. So is that their housing or my housing? Uh-oh, now I've confused myself. It's why I need the bearing in front of me with a micrometer and say, this is what the thing measures and what I'm going to end up with. All right, so the width tolerance was minus 0.5 thousandths. And so what I'm looking at is the ID tolerance could be as small as 374.7. All right, so if I was to make the shaft 374, then I think that's a doable number. So I get a couple of questions on the revolves, and so I want to throw the revolve in. Tried to open the part, and my screens are catching up to me. All right, front plane. We'll open up the sketch. And again, I'm going to provide you these parts if you want to bring your drawing in. You can, up to this point, all of the ID numbers, all of the items should be there. But let me know and we'll back yours up before we start overwriting anything. But I'm going to provide these extra parts and these changes to you. So if you're following along and you can manage them, great. Stay with it. So vertical, infinite length, we'll set it on the origin. I'm going to draw this in the up orientation. I don't need much of a flange, so I don't want to make it too small, too thin. So again, kind of just working through the design process or my thought process. 3/16 ought to be plenty. All right, and with the revolve, I'm basically thinking of this cut in half and cut in half again, so that we're working in a quarter view of the part. So my scaling, and since this is at 1 inch and it will auto scale on the first go around, if I make this 374, and so the consideration is I don't want to have to press this into the bearing, through the housing, through the bearing, and into the other housing. So I'm not concerned about it turning, spinning on this shaft. When I sandwich the bearing, it should still just be the outer race that is doing the spinning with that pulley attached to it. So if we go 374, it didn't quite adjust as much as I thought. And we give it maybe a ½ inch so that I can do a standard stock. And then I need to get out of the diametral, so hitting escape will send me back to a linear. And for size, 1/9. So for ease of manufacture, I'm going to put these at 2 decimal places. And we're going to see what 2 decimal places does to us when pretty much everything else was going out to 3 decimals. All right, so through the body of the part, the stack up, we had the 1/4 inch plate, the 1/4 inch plate, and a max of 220. So that means ½ inch plus 220 would put me out at what, 720. So I want to see what that does in the build. Oh, and I guess it would help put a decimal place in there since that was probably 720. 0.72. That's a little better. All right, so at this point, with revolves, it's going to see this open edge and say, do you want to close your sketch? And I'm going to say, sure. Or I can come over and grab another line, and we'll drag from point to point to create that region. Since there is only one center line, that will become the basis of the revolve, the axis of revolution. So center line becomes the axis of revolution. All of the enclosed region gets revolved. And the only thing that would really change if I took this line out, so go ahead and delete that selection, and I started picking others, I can do pretty much any of those shapes, except for when I come over to this one, it's going to be self-intersecting. This little leg is going to wrap around on itself. It's going to self-intersect. It's going to say, no, you can't do that. But almost everything else is legal. Right, and then I'm going to create a whole wizard. So I didn't grab a button head or a socketed cap screw. Couldn't think of it. So we'll have to, as we go further in and we do our positional tonight, we'll have to build those. Make sure that I have something that actually has some clamping. Or if I need to, I include the length of the screw to have a washer and have it retain. What I don't want, and so thinking through that design process on the stack up side, I don't want this to crush. I don't want it to cinch down on the bearing if we have the tolerance that's not at the same relative scale to those spacers. All right, so I'm going to switch over to the tapped hole, and I'll make this a 1/4 right? So pretty much going to only leave a 1/16 of an inch on each side, but because of the load and the kind of things that I'm anticipating, I'm probably not going to make this out of aluminum. This is going to be a stainless steel part or a steel part, and that way we can have a decent finish and be able to if it does spin, if the inner housing of the bearing does spin on this, it will have some wear resistance. Okay, going over to the positions, because I pre-selected, I can pick the face, and it places the hole. And being that it's not quite an inch long, I'm going to go ahead and just send the hole all the way through. All right, I don't necessarily have to tap it all the way through, but it's not going to hurt anything. It's going to be easier to manufacture. So when I have this in the lathe and I'm turning this to my 374 plus dimension, and I go to tap this, I'm not going to have to worry about when I go in with a parting tool and separate this piece. It's going to go into a drilled hole and fall off. I'm not going to have to go all the way to the center. So there's enough advantages there on the design for manufacturer side to be able to justify a through hole. All right, so that little piece becomes the axle. And since I'm not applying I'm applying names rather than generating part numbers. Oh, well, it's axle now. Then the other thing that I would want to consider is I think we did this with the spacers, but I want to revisit it because it's such a handy tool that on the SolidWorks side, on the design side, as our assemblies become more complicated and we're having to deal with more of these parts and components, is under the reference geometry, you'll have a mate reference. And the mate reference says that I can pick this edge, and when I drag and drop this into the assembly, it's going to see a concentric to this cylinder and a coincident to this face. And I get it by virtue of having that mate reference. So we'll save the assembly one more time. And then when I go to the window, let's tile horizontally. And really it's that one that I need. So I'm going to minimize, and with the screen space, now I can drag from the axle, and I don't have to place any mates because as it locates, as it finds, it will see those geometries. So just like the spacers, this is able to spin, so it's not going to have the it has the minus still in front of it. It's not fixed. It's not forced into that position. But it is at a location to where it's not going to move away. It's not going to drift. All right. So on our through hole, we weren't real concerned about the body, and if I did the math correctly, then I can do a quick select, and nominal distance will be 0. So usually, if I see a 0, I'm relatively comfortable with a 0 down here on the bottom of the screen in the status bar, because if it was 0001, it would probably pop up somewhere. If I wanted to see it to 6 decimal places, we would go over to evaluate, and we can set the measure between those two faces. And then the minimum distance, 1/1000 of an inch, well, that's between, maybe that's the diameter. And where did my screen go? Okay, so let me pull this one in. And so on the measure, when you get the pop-up, we'll expand that out. And I'm seeing zeros. 2 selected items are parallel, and the distance is 1/1000 of an inch. All right, so the 2187, that's about right. All right, so we want to see it go further. And then we can go to the units in precision. Be careful with this one because it does have a side effect of, I don't want to say conflicting, or previously I've encountered where this will override the document units. So I'm only going to turn this on long enough to see my numbers, and then after I'm done, I'll make sure to turn the custom settings back off. So decimal places, let's see what it looks like at 10. Oh, and it went 2 millimeters on me. All right, so let's try inches, and all right, so apparently I can go to 9, 8. We have 8. All right, so distance of 1/1000, so that's in the stack up, and the delta. I didn't expect to see a delta of about 1/1000 and a little under 2 thousandths, or actually 2/10. So that's pretty darn small. So I have to decide how far I want to chase that on the mechanical side, and right now, not too much. So I will go back and turn the document settings off and close those out. All right, so we start to have those tools. All right. The other thing is that we identified that on one side of the plate we have the 1032 tapped hole. So in plate 1, I closed up, and let's see, the cut extrude. Oh, that was the second one. We picked those up. So from the original layout, we set this number as a clearance, right? So somewhere in that sketch, I picked up those geometries, and then when I set the 1032 through, I just picked that as a center point. All right, so to make that change, I have to go back to the layout. So what I want to get to or refer to is that as you're going through this process, if I tied plate 1 to plate 2, which was tied to the pulley, which was tied to something else, we'd have a lot longer line of traceability back through these parts. Having the single layout sketch says, I'm trying to reinforce that single point of failure. All right, so looking at this, the 0.19, when our threaded hole is about 0.187 to 185, is still going to be pretty tight. So when we're looking at this from a positional standpoint, a standard clearance is going to probably be 201, number 7 drill. So I'm going to bump that up to 201 so that we can start looking at the positional tolerance. All right, so make sure it rebuilds and then save it. Oh, and it went over to the other screen, so let me save all, get back into it. All right, so on the screen it lines up, and I will diagnose what I did in here too. And it was probably my stack up of numbers that I got that little bit of shift on this side. But for the most part, I'm pretty happy with the overall design. All right, so anytime you want to see on the interior, we can shift over to the hidden lines visible, and we can kind of see where those line up. And then we'll go back to the solid. And so let's work on that positional tolerance. So as I went through this, I was thinking about, the holes in this plate really aren't that critical, but they do become a datum. So that 375 number that this pin should easily slide through, and then go through the bearing, which is clearance for the bearing. Then it comes down to these holes, and typically you're just going to make it enough oversized, like the 201, all right? Or I take my guess and say, oh, I'll just make it 190 and I'll adjust it later. But at some point I'm going to want to think about what those do, and if I increase the positional tolerances so this can move around, how much can these plates rotate or shift around the spacers around each of the geometries. So on the text, we went through the different levels. We started into the levels, but that's still at that higher level of complexity than I want to get to. And we kind of breezed over the virtual conditions, so now we're ready for virtual conditions. And what the virtual condition says, that our features that we're applying these tolerances to, at some point it comes down to a center line, or it comes down to a midplane that is a theoretical or virtual location. All right, so when we shift over into maximum material condition and we start applying those tolerances, we're looking at it in terms of that virtual center line, that virtual geometry that doesn't exist yet. So one of the last things I want to do is add the fasteners and go through the process of what it's going to look like in the assembly. But thinking about the fasteners, the size of the fasteners, how much clearance and rotation we can get, kind of still starts at this point. So in the evolution of our design, the evolution of getting this out onto the machine shop floor and actually making a part, each of these steps is going to play into that mix. So I'm going to open up an assembly sketch, and I know I'm in a sketch, so I do want to keep the warning on because I do that quite often. All right. So kind of a quick introduction to the position. True position is that we have our tolerance zone, but in effect, the location tolerance is going to be to this center point, not necessarily to the holes. Right? So depending on our inspection method, well, I can take a pair of calipers and I can measure from this edge to the outside, and I can get an approximate. But I know as soon as I touch off on the first part and I drill those holes and I take that piece out and I put the second one in and I drill the second set of holes, just in the process of banking that part into my stop, I have a slight variation. Whether it's 1,000th, whether it's a couple tenths, whether it's exactly the same, we're always going to see that little bit of the fluctuation, a little variation. So what we're trying to do with the positional tolerance is tell it that it has enough room that this is going to be functional in a lot of cases, not any tighter than we need to make it, not any looser to affect the functionality of the part. So when we are doing, let me make sure I'm getting this, getting my head straight on this one, because we said our default is regardless of feature size. If I don't call out a maximum material condition or a least material condition on one of these, each of those modifiers pulls something else into the mix. If this is regardless of feature size, then we're telling it that the position of that center has to be within plus or minus 5,000ths currently, because we haven't set a position tolerance. All right, so that that tolerance will look all right. So if we were doing cylindricity, we could say we have an envelope of let's make it 10, so it's probably still visible. And I'm going to shift that just a little bit over the edge because I haven't really set a diameter for it yet. I would need to go from that edge 5,000ths because we're midline on the edge. And then for our plus or minus tolerance, I'm going to do the center rectangle. Oh, and actually thinking way too big because that virtual condition says that it's actually about that size. All right, so when we're doing 10,000ths, and I lost my dimension. Where did we go? Smart dimension. Okay, why am I not getting a dimension? Okay, maybe just button happy. All right, so plus or minus 5 from that center point would be 10,000ths, and you know, that was kind of one of the starter conversations, is that center point can move within that box pretty much further in the diagonal direction than it can in the horizontal and vertical directions. All right, so our tolerance zone based on the standard dimension, we'll go back over to the pulley sheet, and I'm going to pick that one up. So the 201 through, it updated, it saw the change from 190, we went to 201, and so our tolerance here was the 188 plus or minus 5, 188 plus or minus 5, and that that geometry then looks like, when we come back to the pulley, oh, kick me out of the sketch. All right, so that's going to be fun to get back into with my counter right there. Let's try that again. We'll edit the sketch so we can go left to right and plus or minus 5,000ths, but we're going to have closer to what, about 7,000ths, maybe 7,500ths that we can go on the diagonal. So we're not getting the same kind of condition, the same condition as if we treated this as a circular tolerance. And that's what the positional tolerance is going to do for us. All right, so that's one location, one position. Now let's see what that works out to. I'll say on the trig, 7.5 thousandths, make this dimension driven. Oh, nice, it went to amber. And so, yeah, the 707, we're kind of right there at the same numbers. So, all right. So on the circular tolerance, we're pretty much saying that if I go 10 thousandths, and that just came up tangent, all right, it's either going to be, we're going to fit completely within this plus or minus 5 tolerance, or as our tolerance gets tighter, 2.5 thousandths plus or minus. But we can't stray outside of the circle into this second range with our position. All right, so I'm going to go ahead and save that for a reference, and when I turn off the counter, I'll label it, and that can be your comparisons too. And I do want to hide that back. All right, so again, kind of a quick introduction. It's way more in depth than just saying here's our box and here's the way this thing can float. All right, so what that looks like then is back on the pulley. Let's see, where did that one come from? So to apply a basic dimension, we're going to select our critical here. Let's see, what did we do for tolerance? I really wish I'd done the ordinate dimension on this one. So if I give you the other sheet and you pick it up, you know, just do ordinate dimensions when they get to this complexity. All right, so we set a form tolerance of flatness of 2 thousandths. I said I really didn't care about the other side because whichever side I make flat, that's going to go to the inside and butt up against the pulley. All right, and then I don't want the pulley or the bearing to wobble or you know, be able to rub up against the outside. So this gives me my form tolerance, and in effect, this becomes datum A. So I thought we applied, did we apply that on one of them? Guess not. So I need a datum feature, and I can apply it. Oh, I picked up one of them. All right, and then the thing to watch out for is within our drawing package. I've already used datums A and B on previous sheets. So this one's automatically going to go to datum C. You have to decide if each sheet's going to start over with an A, B, C, or if it's taken as a whole on the document where it goes through C. I haven't found anything that says, you know, through the whole document. If these were all individual sheets and not a drawing package, then it really wouldn't be an issue. It would just start with A. So that being the case, I'm going to go with the let's apply it. And then one of these edges is going to need to be our datum D. Okay, and then another edge is going to be datum E. All right. All right, so I'm going to go ahead and save the document. And then this is where I have to dust off some brain cells and start thinking about how this works in practice. All right, so the 0.188, and then our other dimension, the 4.063, and the 4.813 all become basic dimensions. They need to be modified by this positional tolerance. So when we pick our tolerance and precision, I tell it that it's basic. It gets the boxes. The rest of the dimensions at this point, I may build up, and you know, the question is always, if I just put a note down here, all dimensions are assumed to be basic. Well, a basic dimension is usually modified, so you can make the argument both ways of, well, if it's not being modified by something, why do I need to make it a basic dimension? It's not making it exclusive or calling it out as being something that is critical or to pay attention to. All right, so it comes down to practice and going through the process enough to say this is what works. All right, so we put a diameter of 201, And our position for this, let's see if I can just go right into the GD&T. All right, so clicking on that dimension, I'm adding that tolerance to my diameter. And my screens are messed up again, so I got to go retrieve my properties window for the geometric tolerance. And so if I give this a positional tolerance, then it is in reference to we had a plus or minus 5, so the actual tolerance window will be 10 thousandths. And then our primary will be C. And then if we're going through D&E, but really at this point, do I care about D&E? It's kind of in position to this hole, and I didn't apply a datum to it. All right, so this is where we're still making decisions as we go. All right, so let's see what it looks like with the C, D, and E. All right, so basically we're lining those up. And then the question is to have any kind of the bonus tolerance, which is a whole nother conversation, but basically as the hole shrinks to its minimum value and or grows to its maximum value, how much can that tolerance envelope shift to accommodate the variation in size? Right, so if we go to regardless of feature size, it's just going to look like, and I'm not sure about that one, I have to check into that. Oh, this was a combined. All right, so I got ahead of myself on that one. Okay, C, D, and E was the tertiary. There we go. All right, so is it going to let me have that one back? Probably not. Oh, that's neat. Okay, make sure to click through. And since I'm not combining those up, okay. So each of these are, instead of as a combined, I've got to think what that's called. All right, so instead of being combined together, these are taken individually and in order. So the 10 thousandths, it can't vary perpendicular more than 10 thousandths. Well, that's pretty generous that it can move in relation to our flatness. And the D is in comes back to in relation to the edge, and those are our edges that we've created, so they're not bad, they're just not great. All right, and then I jumped over and didn't do a maximum material condition. So if I need a material condition, then I'm going to put that on as the group. All right, and then notice that I can take it off, and maybe it's maximum material condition in relation to C. All right, so I can go in and I can further refine those, but be careful. The more complicated you make this, the more the interpretation comes down to, all right, really, what is so critical about C that we need to be at maximum material condition, but at C, but not necessarily D and E. All right, so are we applying it to the whole tolerance or just an individual datum? And then on the other end, why do we need these two if that one's so critical? You can go back and forth on all of those quite a bit. All right, so that gives us a location. Oh, and I didn't really want to leave that. I wanted this one, and then we'll come over to this one. And so tolerance to all datums at its at the 10 thousandths, and can hit OK. All right. So did I make that complicated enough? Positional tolerances are one of those fun things that until it gets tight, the locations start to line up, or we start bringing this tolerance zone down to 5 thousandths or maybe to 1,000th, that this becomes pretty critical to the location. So 10 thousandths is fairly generous tolerance for this to move around, but it keeps us in line with the sketch with the plus or minus 5. All right, so in the process of doing all this, I am going to go back and verify that I built these up correctly. And so the geometric tolerance applied to this one will basically be the same, right? They're going to be able to move in the same direction. So a positional tolerance, 10 thousandths, with a primary A, or C, I'm already shifting, D, and E. Okay. And a couple of other things to note. If you needed a note below the frame, we have that over here. Last week we looked at some of the straightness from and to. You can put in your dimensions here. So you have these additional items that you can build into the mix. All right. So we're going to call that pretty good for now. The last one that we needed, we said that we could have a product. I don't think I'm going to do the product dimension, or if I do, I'll do it outside of class. I can bring in the bearing and say, here's the product description, here's its note that we got from McMaster, so it's tied to, or if we're buying it from Timken or NSK, whoever our supplier is, we can put their information in there and say, this is what has been sourced and we're going to accept as our part. So that axle, I'm going to go in the blocks with duplicate names. All right, so basically the third angle projection block. You can already use existing, so no, I don't really want to rename. It can reuse. I brought my picture back on that one, and it still lost it on those. So haven't figured out what's going on with my logo. We'll give it a whatever. All right, so I'm going to go over to the view palette. And I'm going to find the axle. Since it's open, it'll be in the list. And then, let's see, what do I want to do for, let's bring in the front view more so I can illustrate. Wow, that's really big. And then I'm going to put one over here on the side, which really doesn't tell me anything. But that is really big at 5:1. So let's maybe take it down to 2:1. And one of the things with the rotation is if I pick better out of the view palette, I wouldn't necessarily have to go through this process. So one thing I can do is tell it that it is the right side view, the top side, or I can rotate. And rotate is one of those kind of non-intuitive. If I come up to the heads-up display, rotate view, and tell it to rotate that 90 degrees and apply it, it will tell me that the dimensions are going to be deleted. So you do not want to rotate after you have fully dimensioned this drawing. It's kind of at that point, suck it up and live with it. But now it shifts over and it goes to my my dimensions. So that is kind of this end. So what did I tell it? Let's go rotate. I went 90 degrees. Let's try 270, not 2700, and apply. Yes, I'm going to view. And so that's kind of what I wanted, was to be able to have that those concentric circles. All right, so in the view palette, if I had picked a little bit better, I would have probably brought in the top view, and then when I drug the projected view off to the side, it would have given me my geometry, my correction. The only thing is it would be whichever side. It would have been reversed and over here. So whichever. And then I have to make a decision on if I want an isometric view. We can go back to the layout, and under the projected view, then I can get an isometric view. And no, I really don't care about my 1/4-20 tap tool. All right, so that was something that I jumped over on the discussion for the threaded holes. Whether we're going to do functional gauging. We didn't make any specification or call out of, are we going to do the minor diameter? Are we going to do the pitch diameter? Major diameter really isn't accessible in this case. And then, kind of thinking down the path is, how critical is it with a 10 thousandths positional tolerance, and I'm holding a reasonable, class H6 tap. I should be within the tolerance zone and the pitch diameter of everything as we need it anyway. So we're going to stay with that one. And then since I saw the tapped hole here, but it's not really showing up here, so that's interesting. It didn't give me the dashed lines. So let's go through the same process. We're going to put our starter dimensions on it, and we designed for convenience, but for manufacturer, I probably want to pick a standard datum to work from. All right, so if I were to pick up the 0.72 and then do an overall, or if I was picking up the ordinate, then maybe this is my 0 ordinate, and I would give it the overall length. All right, my diameters then, we'll put it on the sides. All right, so this one I said really not that concerned with, and also on the spacer we really weren't that concerned with. I left those in 2 decimal places. So there comes a point that giving that extra tolerance, I can use bar stock. I can use my standard round stock, and if it's a little bit over, a little bit under, I'm telling the manufacturing that it doesn't matter. On the other hand, it would be nice if it was cleaned up, had a nice polished, pretty surface on it. But by doing this, I'm letting it know that I can increase the manufacturability, reduce the costs by saying, let's just go ahead and make this part, leave the butter coat, standard coat, or if we take a little bit, it's not gonna matter if the stock came in at 500 and we take 5,000. Your tolerance isn't that critical. All right, so the tolerance that is critical though is the one that's in the center. All right, so that boss is, if we move it out to the 4 decimal places, then it becomes a 374. And if I'm just going to do this as standard dimensioning, then it becomes a limit dimension or a bilateral dimension. So to me, I like the limit dimension, because if I tell this to go up 0.5 I'm going to see the upper and lower limit. Those give me 2 definite numbers that I can move to. Where I usually get in trouble is because I'm doing math. And it's very easy to get off a decimal point, look at this and go, oh yeah, 374 plus 5. I can go up to 379. No, I can't go to 370. I have to stay within these 2 numbers. So that gives me a slightly better sense of what I want to end up with. All right, so our form tolerances, well, we're not really dealing with flatness here. We might be able to do across the face, but other than we said a set button head or a socketed cap screw coming into contact with this face, I don't really have much need of flatness and parallelism to the ends or perpendicular to the center line. Oh, and since I don't have a center line, let's drop one of those in. And if I pick from there to there, I should get a center line. And since they're not the really annoying magenta, let's go ahead and put them in the center layer. Now they're the really annoying, jump out at you, know that they're center lines. All right. So I still need a form tolerance as my first level of GD&T. And so of the mix, I don't really want to use circularity here, because if I cut this into individual segments, that whole virtual component of the center line can arc or move around, but this can still be circular and within tolerance. This has to be, when we look at the 0.5 tolerance, well, that really puts the crimp on being able to move the center line, our virtual center line. But within our tolerance positioning between these 2, I really don't have anything that's that critical. When it comes down to it, the tapped hole doesn't necessarily have to be on center, it just has to contain. All right, so as we build up through this and we're making these decisions, there's always going to be that plus, minus, plus, delta. What is it that I'm trying to achieve analysis? How can I get this there? So, my natural tendency is I want to make this really complicated and put a position tolerance to the, where are we at, the F datum, which is the outside boss, and I want the center, and then we'll be at the pitch diameter of the threads. It's not that critical. I just need to take a step back and look at it and go, really, I need this to be cylindrical, so when it comes up and it butts against the faces of the plates, this surface needs to be perpendicular to the center line. But other than that, I really don't need anything else. All right, so let's go ahead and apply a cylindricity. All right, because cylindricity is going to say plus or minus 5,000. Well, we've already kind of controlled it with the 374 to 374.5. So my cylindricity is going to be pretty tight here. So let's see, circularity, cylindricity. So if I want to stay in alignment with that tolerance, or at the end of the day, am I duplicating that tolerance having both? Well, yeah, absolutely I am. One of these has to have precedence. One of these has to have priority. So I'm going to put both on there, and then we'll see which way we want to go with it. All right. So if I was to put a half a thousandth, that would be 0.0005. And cylindricity doesn't have any datums. It is a form control. It is the basis. So we need to pick a location for it, so I can apply it to the cylinder. Well, that kind of makes sense. But, to make the argument, or make the argument stick, if I apply it to the same cylinder that I have the dimension on, those should instantly raise, hey, this is in conflict. Something's going on here that, I need to pick. So on the one hand, this dimension makes a lot of sense in the ability to pull that number, but I really need this to be a basic dimension, even though this isn't, the cylindricity isn't really modifying, but I need to put it in reference to that number. All right, so now I got to think through the process again, make sure I'm going down this rabbit hole with a purpose, that it's going to make sense when I get done here. All right, so in effect, based on this information, to control the cylindricity within a half a thousandth, then my mean value, or if I'm going to maximum material condition, at this stage, we're pretty much at the least material condition. All right, so thinking through what kind of condition, what is going to play on into this, is I really need the 370.425. All right, and then I'm going out now to 50 millionths. Yeah, I'm starting to have a little heartache about cylindricity. I mean, I think for the length of 720, I'm going to be able to hold this number cylindrical down the length of it, and I don't know that I need the GD&T. All right, so I'm going to go ahead and pull that one out. I'm going to stay with the numbers, and at this point, all we can do is make it and see what comes out. All right, so this number being that tight, I'm counting on it to control the center line and the ability of this to move more than a half a thousandth. All right, that may not play out, but that also brings it to where when I go to inspect this, I'm not having to set up. And because this isn't my rotating piece, I don't have to worry about run out or total indicator run out. We're just going to, is this a cylinder enough to fit through the plate, through the bearing, through the other plate, and be able to bolt this? All right, so that was a long-winded explanation of how do I get to this point? All right, and where do I draw the line, and what is what is my strategy? Does everything have to be geometric dimensioned and toleranced? And since I'm saying no, it doesn't, I'm going to stay with that. So the one dimension I am missing is a hole call out for the center, and 201 through all, quarter 20, UNC through all. Does it need to be through all? It's an inch. The question that you should always ask whenever you see a through all on a thread is, will the tap reach? A 440 tap will reach about 5/8 standard tap. I'm just throwing numbers out there. Including the lead, including the actual threads before you hit the shoulder, will it reach? Quarter 20 that's neck down, yeah, we can push it through all day long. It's standard spiral point. All right, now we're going on the tooling side, and I'm deciding for the machinist what he needs to do. But I'm giving him an out that, hey, I know that this can be manufactured. If you've got an order of tap, I understand you're going to charge me for it. If you needed a neck down, if you need a specialty item that will reach or an extension, then it becomes part of the game. It becomes part of the process. All right. So the other thing is when we go to put the socketed cap screw in there, then maybe I only need, we're going through a 1/4 inch plate over here. And because this is just a retaining, I would like to have 2 to 1. I don't necessarily need 2 to 1 to the diameter of the thread, but it wouldn't be bad to have it. So maybe I go 1/2 inch on the depth. And then I'm using a 3/8 or a 1/2 inch length of cut, or length of screw length. I'll spit it out. All right, so as we make those decisions and it goes into our purchasing, what is the difference in cost between a stainless steel 18/8 socketed cap screw, button head cap screw that's 3/8 inch long versus 1/2 inch long? Does it become a specialty item? What I don't want to get is one of them that is, it has to be 9/32. It has to be 5/16. The further away we move from a nominal size, our 1/4 inch fractionals, the more expensive it's going to be. All right, and at the end of the day, that's what we're trying for is cost. We're saving the machinist some headache on the one hand of having to manufacture this above and beyond what it needs, and we're saving ourselves the time and the effort, putting the time and effort in now as we're thinking through this process, so that when it makes it to the manufacturing floor, it's pretty much decided. So that being the case, I'm going to open that back up. I'm going to go back into the hole wizard, so editing the feature. And the hole can be through all. I still want to punch that hole through, mainly because stopping, starting, having a blind hole, this is going to be much easier to tap overall, especially if it's stainless and we pick a 303 or a 304, and I really don't want to go to a 316. We're really not at that level of having to have corrosion resistance, all that kind of stuff. But I think, overall, if I tell this to, I drill this through 1 inch, that's a nice, easy nominal number. I'll be able to blast that hole pretty quick. And then when I tap it, I don't have to worry about bottoming the tap. We're not giving it a min, we're not giving it a max. You can pretty much thread it about a 1/2 inch deep, and we're going to be fine with it. So the blind 2 times diameter, or 1/4 20 1/8 of an inch. So let's see, that's in yellow, so that doesn't seem to be the default. How about automatically calculate? All right, I don't think you automatically calculated that, so let's go twice the diameter. We'll go a 1/2 inch, accept it, save it. And what I'm going to see then on my drawing is that it necks down, and that when we go to the hidden lines visible, we'll see the through hole, and we'll see the thread stop. Right? So it's minor things, but I may decide later on that I want that to go all the way through. We can certainly do that. The other side of this is also the assembly. Is whoever is the lucky person that gets to put all 2 of these together, or all 2 million of them together, is going to have to pick up a screw. And if we have 3/8 is a 1/4 inch of engagement, no, 1/8 inch of engagement. I'll spit. And then we go to a 1/2 inch, that would be a 1/4 inch of engagement. Let's see, for a 1/4 20, that's 50 thousandths per turn. Do we do 3.5 turns, or we do 5 turns? Or we pick up the drill driver and we go zip, and it's set to torque and it closes up. All right. So on the further down, it's been bought off, it's gone through inspection. We've started manufacturing these, and somebody has to put the thing together. And then, do I really want them? How many screws am I going to get on a charge? Do I need to take it to that nth detail? Maybe. All right, so definitely we can overthink and drive ourselves crazy with this. So one of the things, the 1/2 inch plus or minus 5 thousandths, this is going to be a, we'll go to the thread depth, and this is going to be a 2 decimal place. All right, and even though we're not going to inspect even to 2 decimal places, it just takes the, kind of the owners off the machinist to looking, really, I got to hold this to plus or minus 5? Don't need to. All right, so that gives us our drawing package. So for the assignment then, you will be either completing this, building out if you've been following along, filling in the gaps, kind of getting it to this stage where we have sheet 1 with our assembly bill of materials. Oh, I didn't put in the screws. So let's do that. We'll take a break and we'll come back. We'll put in the hardware, because other than the bearing being super critical to my design, the rest of the hardware, I'll figure it out. All right, so probably did need to, we'll do the stack up, see if we can get it through. We probably won't get into the tolerance analysis tonight, but we will get the dimensions, the DEM expert as far as we can take it. So take a pause here.